So what I had, oh, I gotta use my pen. What I had done, the last thing was basically say you had something happen at a state or time one, something that happened in between time one and two, and then what the energy state at time two. So we'll see that this fits the concept of this problem I'm about to do as soon as I find a place to drop it. Okay, there's the problem, and I do not remember this statement. And so let me grab this statement. By the way, this should be in our book as well. It's the same book, it's just the one edition back. So if you look at this, he says, okay, well, I'm spitting on the screen. Okay. He says if the cord is subjected to a constant force of 30 pounds, should I turn the light off on that? It's do y'all mind being in the dark? I mean, it's kind of helpful. I mean, I think it's vitamin D. Isn't it vitamin D you get from? But I don't know that. Is that sunlight? Oh, there we go. All right. So here's something to think about. Okay, is if you were going to be thinking about this as we do this, because this concept would drive you nuts if you were going to do this. Think about doing this. How would I do this using F is equal to MA? We're not going to do it, but I can tell you it's kind of crazy to think that. Because you could do it, but it'll be a lot harder. So what we have is a cord is subject to a constant force, pulling it down here, of 30 pounds, and the smooth, it's so there's no friction between these two. So that's the smooth. But the 10-pound is this thing right there. Starts from rest here at A, and determine the speed when it passes point B, so somewhere right there. So if you were going to do this, I'm just going to take a second. If you were going to do this using F is equal to MA, let's say this point right here, the collar would sit there going this way, and the force would pull this way, and you'd have a weight this way. But then when you got up around here, the collar's going at a higher angle, the force is coming here, the weight's going down, and then you're going up in that way. So what you would do is if you would have to integrate this thing along that whole path somehow till you got to B, because the weight will be okay. It's always going in the negative Y direction. The force changes. It's a function of time. So that's awful. And not only that, very time consuming and very tedious. And if you want to do it that way, I'll let you do it that way and we'll look at it later, but I'm not going to do it that way. So we got to pick two times. So we'll say time A and time B. We do not need to find those times. There's nothing in here that says I need to find those times. But I just recognize that those are two states. So in thermo, what they'll call them is state A and state B, meaning that, you know, whatever it is what it is at a certain time. And then, so in other words, in thermo, fluid may flow through a heat exchanger and come out the other end. Then the state is at the beginning and state is at the end. So in this case, I'm kind of hesitant to use the time because that kind of indicates that you may need to find that time, and you really don't. So let's just write the energy equation. And the way I do it is just every single energy term, mgh, plus 1/2. Now, I'm doing something crazy. This is crazy, but it's crazy because you don't see a spring. But this is just me writing everything that's there. And then 1/2 mv mv squared plus sum of all the f's dotted with the s's from state A to state B. So this is the energy at state A. There is no spring, but I've included it to make the equation complete, because really, you're going to have those three terms. You're going to have energy because you lifted it above a datum. If there's a spring involved, and there's not here, then you're going to have that. And then there's always going to be some sort of velocity. But then what happens is you get to state B, which is the same equation. And I'll go back and add something to it in a second, but give me a second. K S squared plus 1/2 mv squared. And this will be basically the energy at state B. Now, to kind of fit that, I need to put a little subscript there. And then a B, because the M and the G won't change. The spring stiffness won't change. There isn't a spring, but I'm just writing the entire set of equations just to be complete. So now I've got to go in and determine each of these terms. This one, that one's easy. That one's not so bad. So the first thing he says, let's stare at state A. He said starts from rest at state A. So that pretty much says 0. Now, since there's no spring, I don't know which one you could say is 0, but the whole term is 0. The whole term is 0 here as well. Now, the next thing is this one needs a datum. So to me, I always find it convenient to find the lowest spot and say that's the datum, because then I don't have any negative numbers. I just don't like negative numbers in using the datum. However, you can do it this way and put your datum here. It's just that when you do that, you're going to have a negative number being 4.5 there. And so that's up to you if you want to do that. But I'm going to pick the lowest. And so all I get on the left side is this, mg, but h is 0, so I get 0 because all of these are 0, plus sum of the forces. And I'll deal with this in a second. And I shouldn't do, it'll be okay. I shouldn't use the same symbol here that I used there, because they're not the same. So maybe I should do something like a delta. How about that? No. How about an S here? How about a delta there? What did y'all do in physics? What did y'all use in physics? X? Or did y'all use a delta? When you did the 1/2 K delta squared, or X squared, or... Oh, it was X squared? Okay. All right, well, I could put it in as X, but then that would confuse with the X there, but I don't know. I'll leave it as delta right now. I don't really know. And then I got to find the MGH at B, and then the 1/2 MVB squared. So all I've got here is the energy imparted by this rope here, this 30 pound, is going to be responsible for creating the energy that's associated with those two terms. So now I need to deal with all that. So what I'm going to do is, now that we've done that, I'm going to take this and move it to the side over here, and move that other one up so I'll be close to the diagram. So then when I'm here, I'll move this back up along in here so I can start working on using the diagram. Be closer to the picture in essence. So the first question, let's do the second question here first. The mass of this thing, okay, so the force is 30. It's a 10-pound collar. So believe it or not, mg is equal to 10 pounds. or the mass of, if you think about it, that's all it is. It's the weight of the thing. So mg is the weight. So I just put 10 pounds, and I can put the pound. I guess I'll put the pound. And then it moved up 4.5 feet. And then I've got, now here I can't get away with this. I've got to use the 10 pound divided by 32.2. And that's because if this is 10 pounds, then the mass, G is 32.2 feet per second squared. So M is going to be equal to 10 over 32.2, and that's going to be slugs, the weird unit. But and then I'm going to have the velocity of B, and that's what I think he wants to know. What he says, determine the speed as it passes point B. So here's the key. What do we do here? Because we have this thing, it's, you know, here it is, it's a long rope, it reaches all the way to here, and then what happens, it gets up to here, and it's pulled straight here. So it's very confusing, except there's something interesting here. If I put a dot or a piece of tape around the rope, then the rope itself had two particular pictures you could look at. And I'm going to see if I can do both those side by side. And I may have to move them. So here I'll say state A. State A isn't this, it's the block sitting here, and the rope goes over to here and then down here. So let's say we did this and we put a piece of tape right here. So here's your piece of tape. So how long is this rope from here to here? Let's say it's 1, 3, and so that becomes 6, right? And it's still 4.5 up. So my contention is that that rope length right there is going to be 6 squared plus 4.5 squared and the square root. Now, I've been using this thing, and it's been good because I don't have to monkey around with a calculator, and that's the, I hate to advertise for anybody, but it's just the photo math thing. I'm not advertising for anybody. So it says that thing is 7.5 feet long. Now, if you think about it, say it's state B. So what happened between A and B, it does concern us, but we're looking at the energy that it took to get from, or that the force is imparting from A to B. There was no friction on this thing. So there's no, and that's advantageous because the friction on the, if adding friction here would be awful. But the length of the rope here is such that the piece of tape moved all the way down to here. So here's my piece of tape. I just put a piece of tape. Maybe I put the piece of tape right there. So here we go. Let's put the piece of tape right here. So here's my piece of tape, blue tape. Now my blue tape ended up down here somewhere. So how far did it go? Because it was sitting right here. It ended up right here. How far did it go? What's the distance the piece of tape went? Well, I know from here to here is 2 foot. So I contend that looking at these together, that the piece of tape moved down 7.5 minus 2, or 5.5 feet, is how far the piece of tape moved itself down to there. Does that make sense? Does that seem reasonable? Now, what's weird about this term right here is that it's applied to the system, and it is actually applied to this mass, but actually, if you think of it, it applied 30 pounds as it moved along there. you don't care too much about it because it's always 30 pounds and it moved a certain distance. So it was 30 pounds. So think about it like this. Here's the piece of tape. Okay, so let's just imagine we have a piece of tape. We're pulling the piece of tape 30 pounds. And then the piece of tape ended up down here, still being pulled with 30 pounds the whole way, but it went in that direction 5 feet. So that would be in the same direction. So F dot S would be 30 pounds applied through 5 feet, or 150 foot-pounds added to it. So it would become plus because this, the force and its movement, S, are in the same direction. If you think about it, if they're in the same direction, F dot S is equal to the magnitude of F, the magnitude of S, times the cosine of the angle between them, which is just 0. So that term just becomes 1. If they were moving the opposite direction, like friction, so you had, well, actually, friction, you would have kind of this. The S would be going that way, and the friction would be saying, I'm slowing you down. Then F dot S would be F S, and then cosine of 180, which that will become minus. So in fact, this term is plus because it's adding energy to the system. And so if it was friction, and we've seen that before, friction takes away because of the dot product. Yeah. Was it 5.5? Oh, sorry. Duh. Okay. My mistake. Yeah. That makes it complicated math, isn't it? Is that 150? It's 165? Is that right? I think that's right. So, sorry about that. That was just a complete omission on my, because I said that 5 seconds ago. Maybe I said it 5.5 seconds ago. So now you've got this term, which now I've got this all pushed together. So what I'm going to do is I'm going to slide this over, maybe down under here. I think if I touch this, it just goes down there. Okay, so I'd put that down here. But now I take that 165 and put on the left side. And so if you want to know the final velocity, give us a second here. 165. I got to take off. I think that becomes 45. And then I have to multiply times 2 and 32.2, and then divide by 10. I'm moving. So what I'm doing is moving that to that side, and then I'm dividing this out, taking the square root, and that should become velocity of b. Now, if I move that over to the right, I can use that thing and probably get the answer, except it probably won't understand what that is. It may understand the rest, but there's no guarantee of that either. Let's see what it does. You have to look and make sure it saw what you wrote. I think it saw what I wrote. Velocity of b was equal to 27.7 or 27.8. That's good enough. Now let's throw monkey wrenches in it since we got it here. So this will be an answer. This is your answer, and then you turn around. Let's just say, out of curiosity, that I know this is not exactly a reasonable thing, but, and notice something else too. We never really needed that, although that's nice to put there if you want to. It's nice because if you want to use some of the forces equal EMA, you probably need to know that, but we don't want to know that. So in any case, let's say we did something like this, where this was in say instead of 4.5, it was something like taller. And let's say if we did that, if it was taller, just out of curiosity, this would become larger. Say it became so large that this term became negative. What do you think would happen then? So say this became negative. Then what that's going to tell you, so essentially it'd be kind of like a block sliding up a plane. It's going to reach a point in which it went to that point where the velocity ended up being 0, and then it started heading back down the plane. So if you're looking for the velocity, say, up a little higher, so you say, what happens, what's the velocity when it reaches this height? Well, if it never reached that height, you're going to get velocity v is equal to the square root, and it'll be a negative number in here, meaning that you never reach that height. Then the next question you should ask is, how high did it actually go? You know, does that kind of make sense, or did I throw too much of a monkey wrench in there? Maybe I shouldn't have said anything like that. But let's go find a problem that's actually, I can't guarantee that I can find a problem that's actually like that. But we got 2 blocks here. I could do that one. And that one has friction. Let's do that. That ought to be, let's see. I'm going to get the pictures individually. I just do it at the bottom of this. So here we go. We'll just put it right here. Oh, the picture's kind of tiny. But it's okay. Yeah. Let's we could do that, or maybe zoom it. I don't know. Let's see. Okay, so we get to there. There we go. That'll work. Plus, then let's see how thick my pen is. The pen's, because what happens, I've noticed this. You get too far out, the pen becomes so thin, it's almost non-existent. So this time you got 2 things. Okay, so 2 blocks, A and B, have a weight. Oh, they both. Oh no, they don't have. But they don't have the same weight. Weight A is 60. Okay, and then weight B is 10 pounds. If the kinetic friction between the inclined block here is 0.2, determine the speed of A after it moves A. Determine the speed of A after it moves 3 foot down the plane, starting from rest. So you can't get away with this without this. And that is, when you got friction, you still have to kind of do sort of a free body diagram. So I got this. I got this. The thing is, really what I'm searching for this time is the normal. And let's think about this. This angle and that angle should be the same, because of a variety of reasons, but one of which, this one crosses the perpendicular to that. In other words, that's perpendicular, and this one's perpendicular down here. But then the other thing is, you can envision this angle collapsing. Say the inclined plane started moving down. When they coalesce to 0, these 2 would be the same. So that's another logical way of thinking about it. So what you're wanting to figure, this is 60 pounds. So I can get rid of the 60 pounds up here. So the normal is going to be, well, the 60 times the cosine of whatever that angle is. Now, if you look at the cosine of this angle, which is the same as that angle, it's going to be 4/5. So this is going to be 4/5. So it's going to be 60 times 4/5. Let's let's see, 4 knock away that. In that 12 and then 4, it's 48. Is that right? I'm moving into some difficult territory for myself. So that's 48. So that means this block he is claiming is going to move this way. If it does, then the friction force has to impede it. And it said it was 0.2 times the normal, which is the normal becomes, okay, so 0.2 times normal, that would be, let's see, 4.8 and 4.8. What's that? 16. That's 8, 9, 9.6? 9.6. Am I thinking correctly? So you got to get that. Now, we know we can do this one easily with F is equal to ma. So how do we do it with the other being the energy thing? So this time you got two masses. So what you're looking at is, again, this time I'll call it time one or state one. And in state one, I got two masses since they were starting from rest. Somewhere in there, it says they're starting from rest. Okay, it's where I underlined it. Okay, so starting from rest. Okay, if you don't mind, I might skip the spring equation because I don't see a spring here. So VA squared plus 1/2 MB VB squared plus MGHA plus MAGHA MBGHB plus the sum of all the forces dotted with their distances. I do not have an external force. Now I do have tension in here, and here, and here, but I do not have an external force with regard to, well, I actually do with regard to the friction, but I don't have anybody pulling the mass this way or pulling it any particular way. So I do have a force that is occurring between state one and state two, which is time one and time two. That's the friction. So I have to eat my words there. Now what I'm going to do, I'm going to do this. If I can keep my finger on that pen, I'm going to do a copy, and I'm going to say equals to, and I'm going to drop it right there. Now, technically in the book, what he will do is he will identify these with a subscript that deals with the state you're in. In other words, time one, time two, whatever. What I'm going to do is put it on top. At time two, which is the one he's talking about, and that's the one that it moved down the plane 3 feet. So if it moved down the plane, so this is time two is at the point where it moved down the plane 3 feet. Plane 3 feet. And that's my state two. And that kind of defines what state two is. So now, first thing I'm going to do is I'm going to go back and attack each one of these terms over here in state one. Easy for these because he said everything started from rest. Now, this is quite interesting here, these two. And let me show you by copying the thing again and recognizing something interesting about the whole thing. So the first thing I'm going to do is I'm going to change my mode and do a clip. And this time, I am going to take this one. Then I'll go all the way to there. Okay, go back to here. I'll just put it right there. And then I'm going to go to the other one and clip it as well. Let's see. I can clip it, kind of slip down here, and then drop it right in here. And so here's the interesting thing. You can tag any particular spot on here. I'm just going to tag this point, and I'm going to tag that point. And I'm going to say this point moves down 3 feet. Okay, so let me make it long enough. So, okay, so this is 3 feet. So the block A will actually move down this number of feet. Now, that triangle and this triangle should be the same. I wish he would have said 5 feet, because then that would have been 3 and this would have been 4, but he just wanted to be whatever. So this is 3 times 3/5, and I don't know. That's really annoying. Why he didn't make it 5 feet? Did he not make it 5 feet? It would have been so much more clean, but so it moved that far down against gravity or with gravity. So the key is, and this is what's so interesting, you got 2 points here. On A, the datum of A, so I'll say this, datum of A is all independent of the datum of B, because what's going to happen, this is going to move up so many feet, and we don't know what that is. We know this is going to be state 1. We know that's going to be state 2. We know this is going to be state 1. That's going to be state 2. I don't know what that is. I do know what this is. Dust is falling off of it. All right, well, I've kind of avoided, but I'm going to go ahead and, what is 3/5 of, is it 1.8? That's really annoying to me, but I can accept it. I would have made the problem with 5, but that's okay. So now the question is, which datum do you want? Okay, so here I'm going to do something interesting. I'm going to do my the way I usually do. I'm going to pick my datum this way. So that's my datum. So this means H at 1 on A. Here, I'll do it this way. So I have HA and HB. So I'll say H1, or I'll say HA at 0.1 is going to be equal to 1.8. Then HA at 0.2 is going to be nothing. Now, how far did this move? So this is where those rope equations come in. So these things, you still can't get away without them. So here, I'll do like this. I can do this in this little area up here. So here's your SA. Here's your SB. So I see 2 ropes. The length of the rope is equal to all the extra parts, like right here, and right there, plus 2 of these, 2 SAs, plus an SB. Now what I'll do is I'll take a derivative, just one single derivative, and these don't change, so I get 0 is equal to 2SA dot plus SB dot. If in 1 second this SA moved down like it said it's going to move down 3. So let's say it did it in 1 second. So it moved down 3 feet. Oh, wait, is it in feet? Yeah, I think it's in feet. 3 feet in 1 second times 2 plus SB equals how much in that same 1 second? 2 to 3, 6 still, right? So that means SB had to move 6 up. Does that make sense? So you got 6 up. Hang on. So now I got this, which it's not the scale, but it's 6. So I'm going to do this. I'm going to make my datum up here. So the datums do not have to be the same. So I can set up a datum for B, which is this block here. So I'll say HB, and I'll say 1 is equal to 0. HB2 is equal to 6. So now I got to keep track of this. So really, what I should do is put 1 here and 1 here and 2 here and 2 here. For that matter, I should put a 2 there and a 2 there. But we'll go ahead and for that matter, I'll go ahead and put a 1 here, 1 here, but it doesn't matter. But what you see is now I've got the thing that I can put in here. So I got to be real careful. I don't remember. One of them was 60 pounds. One of them was 10. So A was 60 pounds, and this was 10 pounds. So if I take these down, okay, I got to be real careful here. 60 pounds times A, I'm going to write it down first this way, plus 10 pounds times HB at 1. And then I'll put these other terms in there in a second. But I'm going to be real careful. HA1. So that's 60 at 1.8 plus 10. And I look over here and I see a 0. Okay, now I'm going to do something interesting. I'm going to take these two down. So I'm going to move the equation over there in a second, but I'm going to put it real close over here. 60 times HA2 plus 10 times HB2. So what do those end up being? I got to be real careful. HA2 is just 60 times 0, and HB2, 10 times 6. Okay, so now what I'm going to do, did I do that right? I hope I did. So now I'm going to take this and copy it over here wide enough away so that I can put in the middle here plus sum of the force dotted S, sum of the force dotted S. And then what I'll do is I'll do this. I will copy, just do a copy, and I'll do a paste right there, and then another paste right there, maybe, and then try to, uh-oh, is it time to go? I'm not moving very fast, am I? Oh, it is. Well, I guess I could just pick it up where I left off. Because, I mean, I got it right there. It'll pop right back up. I just complete the problem. So, I guess we'll see you Wednesday. We'll start another day. We got really, okay, we got this class period Wednesday, Friday, Monday, Wednesday. Then we got yeah, it got weird. It's a weird thing. We got Monday and Tuesday so Tuesday is actually Wednesday. I don't know. So we got enough class periods to finish all this up. You may find most people find the impact the most enjoyable. Yeah, I'm gonna go ahead and do that. I don't know. Let me find out.